is powering gamma ray burst by the rotating black holes. So this work has been done in collaboration with G. Brown and Ralph Byers at Stony Brook when I was in sabbatical leave last year. First, I'd like to show some of the lists of observational results of the gamma ray burst, which I think are relevant for our discussion on the powering gamma ray burst. The event rate of the gamma ray burst is one event every year, which means approximately 300 per year, which means in terms of the astronomical unit is 0.1 to 0.3 event per mega year. And also the spectrum is, as you noticed by the gamma ray burst, it is the gamma ray. The energy is from few kilo electron volt to mega electron volt. And the most interesting thing is that the spectrum of this gamma ray burst is not the thermal spectrum. So this gamma ray should be emerged at the optically thin region rather than optically thick region. And also by the optical telescope observation, some few of the distance can be measured by its redshift analysis, and it's really cosmologically far away from us. And the duration of this gamma ray burst is from about the millisecond to maximally a few thousand seconds, although the 1,000-second duration gamma ray burst is very rare. And the temporal structure, that means that the burst has not the smooth temporal structure. It has a very small peaks inside, and the temporal structure is such that the delta T is at the millisecond, the edge or the peak. So it means that if you do not want to smear out that kind of the temporal structure, very small temporal structure, the size of burst should be less than 10 to the 7 centimeter. So historically, this arose the problem of the compactness problem. And after the gamma ray, the astronomical observations are followed, and X-ray and optical and infrared radio afterglows are observed. And also recently, the beaming is observed. First, direct observation from the Hubble telescope was done for the GLB 99, January 23rd, and they observed the break in the spectral flow, temporal flow, and also recently the gamma ray burst of the May 10 has been found to have a beaming structure. So this is some of the observational results for the gamma ray burst. And since the observations are for the gamma ray, so there have been developed some very interesting model. I think this is the very standard nowadays, which is a relativistic fireball model. The essence of this model is that the emitting region of the gamma ray is not this center, but the far away from the energy, the origin, which is estimated 10 to the 13 centimeter for gamma ray burst, up to 10 to 16 centimeter. And there are according to this model, there are three kinds of shocks. The inner shock produces gamma ray that we are observing, and external shock emits the X-ray for the afterglow. And also, recently, for the gamma ray burst, January 23rd, the reverse shock is believed to produce the optical flash during the gamma ray burst. And also, the important constraint on in this model is that the fireball should have very low baryon loading, because this fireball should be expanded relativistically very fast. For example, gamma factor should be greater than 100 up to 1000. So the baryon loading should be very low, approximately 10 to the minus 6 of solar mass in total. Sure. No, it's not gamma ray. It is not soft to gamma ray repeater. It's just a gamma ray burst. Gamma ray burst. I'm sorry? No, in this model, yeah. So the total energy of the gamma ray burst is about 10 to the 54 Earth if it is emitted isotropically. So it's enormous energy in a very short time. There is in a less than 1,000 seconds. If you compare the radiation of the sun for the giga-year, more than giga-year, okay. So the one thing you don't have to look at it, consider is that what would be the energy source of this enormous energy in a short time. So one of that is topic of this talk, and we'd like to present that it might be the possible origin of that energy is the rotational energy of the black hole. So this is one summary of that, the energy, and yeah. So the black hole is defined as mass and angular momentum. For the moment, we don't consider the charged black hole. I think the charged black hole case will be discussed more in this conference. So there's a curved black hole, and the A is the specific angular momentum, and A tilde is the angular momentum parameter, which has no dimension. So if A tilde is equal to 1, then the black hole has a maximum angular momentum. So the available energy of the black hole system are two kinds. One is the binding energy of the accreting matter, because if there is a black hole, the materials are accreting from the infinity, and the binding energy is defined as the energy of the last stable orbit. So because beyond the last stable orbit, the matter falls freely, so there's no radiation, so that energy can come into black hole. So the subtracting that the last stable orbit energy, one can find this binding energy, which is 0.06 to 0.442 times the mass of the incoming particles. So the 0.43 is the maximally rotating black hole. So the maximally rotating black hole, one can extract the 42% of the rest mass of the accreting material. The energy is the rotational energy, which has been discussed a long time ago, and we heard some story about it at Rome last week from Remo. So the rotational energy is just the difference of the mass of black hole and the irreducible mass of black hole, which is defined by in terms of angular momentum. And the explicit form of this energy is like this. So So for the maximum rotating black hole, it is 29%. So if you use this value, then the maximum amount of energy that can be extracted out from the rotating black hole is 10 to the 53rd Earth for the solar mass black hole. But I'd like to stress now that we don't need the whole 29%. We don't need the extreme black hole. What we need is the appropriate energy for the gamma ray burst, so that we may satisfy with the 10% or 20% of the black hole. So actually, the extreme black hole cases might be very rare, and we think that the usual case should be around 8 till equal greater than 0.5 or optimally 0.7, something like that. And the black hole has two advantages for gamma ray burst, as I showed you in the previous transparency, that low baryon pollution is very important for the fastly expanding fireball. The presence of a horizon is very special, that the baryonic material can be accreted very rapidly into the black hole. And even the existence of a rotation axis for the rotating black hole, along the rotation axis, the angular momentum is very low, so that it is very easy the material can be accreted very fast along the rotation axis. So it is very, I think it is very easy to make just at least the baryon-free funnel along the rotational axis. So that is the way where the gamma ray burst energy can be extracted out without the baryon pollution, without any baryon loading problem. So this is one of the numerical calculation for the merging neutron star and merging black hole neutron star case, how the baryon-free funnel can be achieved. This work is by Janka Raffat and Janka. They are developing the powerful numerical technique to simulate how the black hole and debris system can be emerged. So now the few words about the rotating black hole. So the rotating black hole is defined as angular momentum and the mass, and A is the specific angular momentum, and the metric is defined as like this, and all the metric, and beta is alpha is the Labs function and something like other things. And the metric, the essential point is that the metric is dependent on the mass and angular momentum of the black hole. And the horizon is defined as the zero of Labs function. And the angular velocity of black hole is defined as in terms of horizon and angular momentum and the mass of black hole. This formula. So with black hole, rotating black hole, I think we can have enough energy for powering the gamma ray burst, and also we can have a baryon-free funnel along the rotation axis. And also one of the important points to be discussed is the event rate of the gamma ray burst. The event rate is, as I told you, one event every day. So it is very difficult subject to discuss, and I'm not the expert in this area, but I'll quote one of the recent work with my colleagues, done by our colleagues, that the binary merger or hypernova can be emerging at the final state as rotating black hole plus accretion disk. So the rotating black hole emergence of rotating black hole and accretion disk rate is related to the binary merger or hypernova explosion. So recently there are many the people who are experts in this area, but here I quote one of the works done by Hans Bethe and Brown. They are using very simple formula rather than using the heavy computer code, and they found the merging rate, which is, I think, consistent with the gamma ray burst rate. If you assume that the binary merger hypernova in this rate results in the rotating black hole plus accretion disk. Then the question now is how to tap the energy of the rotating black hole. Who can extract out the rotating energy of the black hole? One of the simple thing is to use the tidal force, which has been discussed in the different contexts. But I'd like to discuss a little bit about the Blandford-Znayak process, which are using the magnetic field on the black hole to extract out this rotational energy of the black hole. So this is the Blandford-Znayak process. And before going into the detail of Blandford-Znayak, I'd like to show the very simple formula, which even the freshman can understand. Let's just suppose the rotating sphere with current on the surface, which is immersed in the magnetic field, let's just consider the magnetic field which is perpendicular to the conducting sphere. And this sphere, it feels the torque because of the current and the magnetic field, the simple Lorentz force. And the torque exerted by the angular strip is just proportional to the current and the magnetic field and the surface area of the annular ring. And this is simply just the flux through that strip. So the power is just the angular velocity times the torque is just current times angular velocity times the flux through that the angular ring. So this is the very nice formula. And this formula is in fact valid for the rotating black hole. Is proved by the Blandford-Znayak in 1977 using purely they don't use this analogy, but using just the general relativistic consideration of the magnetic sphere. So I will sketch briefly the formalism of the Blandford-Znayak process. The thing he assumed is that the force-free magnetosphere. It is somewhat generalization of the degenerate condition for the pulsar magnetosphere. So I think I should be very quick. The vector he used the vector potential, and the magnetic flux is. This is the case where the axial symmetry is assumed and also stationary case. So stationary axial symmetric magnetohydrodynamic case with force-free condition. And the magnetic flux can be identified as the toroidal component of the vector potential. And the force-free condition leads to a very interesting result, which is that the electromagnetic, the magnetic field is rotating with the black hole with a different angular velocity omega f, but the omega f is constant along some surface which we call the magnetic surface. The magnetic surface is defined as this the magnetic surface. So along this magnetic surface, the A phi is constant, and also the angular velocity of the magnetic field is constant, and the magnetic flux through the surface is constant all along the surface. And the current conservation also leads to the expression for the current between the two magnetic surfaces, which can be related to the toroidal vector potential in this formula. And the inhomogeneous magnetization with source term here leads to this relation, which relates the current to the toroidal magnetic field multiplied by the radial cylindrical radius of this system. Then the power at infinity can be easily calculated by just appointing E cross B flux. So this is flux. So what we are interested in the power at infinity, where we are observing that power. So this can be calculated to this formula, and the formula leads to this the last one. Right? So you see that the power is proportional to the angular velocity of this magnetic field and current times the flux. But as I told you that the omega f and I and psi are constant along this magnetic surface. So one can calculate that quantity which are conserved using that the power with this quantity at the horizon. That's the use of the horizon in this Blandford-Zinaia process. So you can calculate the power at infinity using the quantity defined at the horizon. So this is just the formula that I showed you for the conducting sphere in the magnetic field. So this is the sketch of the Blandford-Zinaia process. And when we can calculate the power using that formula, and for the optimal case where the magnetic field line angular velocity is about half of the rotational angular velocity of black hole, is just can be given with this formula, which is 1.7 times 10 to the 50 erg per second, which is the relevant power for the gamma ray burst. We need the magnetic field. The role of the magnetic field is twofold. One is this is the way. So the magnetic field give us the way how to extract the rotational energy, and the strength of magnetic field determines how fast we can extract out the black hole rotational energy. The stronger the magnetic field, we can extract out more fast than weaker the magnetic field. This is so this is a total mass of black hole, and this is an irreducible mass, which is related to the entropy of the black hole. So the rotational energy is just this difference, m minus m irreducible energy. And for the maximum rotating black hole case, this is 29% of the whole black hole mass. But in the process we discussed by the blank hole denial process with a strong magnetic field, the process cannot be adiabatic. So it's very rapid process. So the process cannot be adiabatic, so the entropy should be changed and it should increase as we are extracting the energy of the black hole. So if we use the optimal case, we can draw like this diagram, like this. And in the general case has been discussed by Okamoto 92. So while we are extracting some of the rotation energy, the irreducible energy, the mass of the black hole should be increased. So we cannot extract out the whole rotational energy. So for the optimal case, we can extract up only 9% of the total mass, not the 29%, even in the extreme case. But if you want to extract out the 29% completely, then the process should be very slow. Then that is not relevant to the gamma ray burst. We can extract out the whole rotational energy without increasing or just increasing slightly the entropy, but the rate of the energy extraction is very slow, and that is not relevant for the gamma ray burst. Now the problem now is how to thread the magnetic field on the black hole surface. Because the black hole cannot maintain the magnetic field by itself, the magnetic field diffuses away very quickly. So we need some other object which prevents the magnetic field from diffusing away. So the natural thing is to think about accretion disk, which is magnetized around the black hole. The accretion disk for the gamma ray burst has two features. First, the lifetime of the accretion disk should be longer than the gamma ray burst duration time, and also the strong magnetic field is required on the accretion disk. So let me discuss a little bit about the magnetic field on the accretion disk. The first, the upper limit of the magnetic field can be obtained by using the equipartition argument, which says that the pressure of the magnetic field cannot be greater than the pressure of the disk itself. Recently, numerical calculation using the hypercritical accretion rate, I think it's done by Usuri, Popan, and Fryer recently. They show that the pressure of disk can be as much as 10 to 30 erg per cubic centimeter, and which is equivalent to the 5 times 10 to 15 Gauss. So at least the 10 to 15 Gauss is not beyond the equipartition argument. But the delicate thing is that if we consider the accretion dynamo, that means the process can create a magnetic field. The numerical estimation recently shows that the viscosity parameter is too low, such that the magnetic field, due to the dynamo mechanism, can be as large as 10 to the 13 Gauss. So so 10 to the 100 is missing there. But the accretion dynamo assumes that the magnetic field is produced only by the accretion process. But disk, yes. Okay. And we are suggesting, or this is not any statement, or it is our suggestion, or it is our wish, that the recent observation of magnetar showed that it has a temperature 15 Gauss. It has been estimated by observing the period changing the observation. And if we assume that this accretion disk can be made out of the material of the magnetar when it is disrupted. So this is a possibility that we can have a high magnetized accretion disk, but we are not sure whether this is possible or not. But this shows the possibility that we can have a strongly magnetized accretion disk, at least.
In this case, the magnetic spectrum will be very flat.
Maybe I'm not expert. You may be right. Okay. If the accretion disk is magnetized, then the same mechanism holds for the accretion disk, and this accretion disk also powers the gamma ray burst. So you can also calculate the power from this accretion disk. So the rotational energy of the accretion disk can be extracted out by this Blandford-Nyack-like mechanism. So for the Keplerian approximation, this power is proportional to the mass of the black hole. Mass is the black hole, and the magnetic field square, and times the inner edge radius of the disk. So now we have the rough idea about the central engine that can be powered gamma ray bursts, and I will show you very schematic diagram for this gamma ray burst central engine. So this is the horizon, and the magnetic fields on the black hole and on the disk, accretion disk, and along this field line, the rotation energy of the black hole and the accretion disk can be extracted out, which about the relevant order of magnitude for the gamma ray bursts. And this is assumed to be force-free magnetic sphere. And this is a very simple schematic figure, and we should add any physical, more complicated nature on this diagram. For example, as we heard this last week, or this week or so, by Pansali and also Chakrabarti, about the disk, accretion disk, which is not as simple as like this schematic diagram, and also there should be some more physics in ergosphere about when the magnetic fields are threading on the ergosphere in this transition region. So in the transition region, the magnetohydrodynamics is very important, and there are several works on this by Pansali and Takasi, starting 1990, and recently also Gami shows some work on this transition region, how the magnetic field can be used to extract out the rotational energy of the black hole. In the transition region, the transition region relates the current flows into the black hole, and the current that flows into the inner edge of the accretion disk. If we use the boundary condition, which is well known for the black hole and on the disk, then we can relate the strength of the magnetic field on the black hole to the magnetic field on the accretion disk. It is very, if somebody is interested in, I will explain more later. Then the magnetic field on the black hole horizon is always greater than the magnetic field on the disk if we assume the current conservation through this transition region. Also, there are interesting results. This is for the black hole case. Result on this magnetic field on the black hole, where the Pescara talked about this morning, that the magnetic flux is expelled by the rotation of the black hole. So for the extreme case, there is no magnetic flux through the rotating black hole. But the flux depends on the 1 minus a tilde 4. So this effect is only considerable only near the extreme case. So since we are interested in the gamma ray burst, we don't need that the extreme case. We can have say that this repulsion is not so effective, let's say for the rotating black hole of A is 0.5 black hole mass, then the total flux is reduced only by 6%. The other thing we should consider is that this argument is based on the environment is assumed to be the vacuum around the horizon. So what Magnetohydrodynamics process is assuming is that the first free magnetosphere, or at least the degenerate magnetosphere, which is full of charge and current. So we don't know whether this formalism can still apply in this Magnetohydrodynamics environment. Okay, 5 minutes. The next thing we should consider is the accretion rate, because if the accretion rate is too fast, then the lifetime of the accretion disk is shorter than the gamma ray burst. So it matters because the high magnetic field on the accretion disk can extract out very effectively the angular momentum of the infalling material. So accretion rate is accelerated by the stronger magnetic field. We calculate with a simple accretion model. We calculate the accretion rate due to the strong magnetic field on the disk. So we use the steady state accretion and the Keplerian approximation. I think this is as far as the angular velocity is concerned, this Keplerian approximation is a good approximation. And then the accretion rate is about 6 times 10 to the 4th solar mass per second. It's a very the super-Eddington limit, very high accretion rate, but it is still relevant for the lifetime of the accretion disk when compared to the total mass of the accretion disk. For example, if the 10 to the minus 1 solar mass for the accretion disk, that can exist up to 1,000 seconds with this accretion disk rate. And also, the current in the transition region is very high, 10 to 20 ampere for gamma ray burst power. But if you convert it to the mass flow, assuming that the current carries electron, then the mass flow is just 10 to 32 erg per second, which is much less than the accretion rate. So in the transition region, this current does not affect the accretion rate much. So in this simple analysis, the accretion is stable against the gamma ray burst power. So I discussed some of the important aspects of this Blandford-Zerniak process, and I propose the possibility of having accretion disk plus rotating black hole as a central engine for gamma ray burst. This is a summary. The conclusion or our wish, because there are many things to do in the future. The central engine for the gamma ray burst, the proposed structure is a rotating black hole and accretion disk, and the power and energy has come about as a Blandford-Zerniak process, as a point flux. So the optimal case, 9% of the rest energy of the black hole can be extracted out in less than 1,000 seconds if you assume the 10 to 15 Gauss on the black hole. And the formation rate of this central engine can be calculated using event rate of these merging neutron binaries or the rate of hypernova explosion, and that is quite consistent with the gamma ray burst rate. And the black hole, the emerging black hole due to this binary or the spinning hypernova explosion can naturally lead to the high angular momentum of the black hole. The simple calculation shows that the A is greater than half of the maximal angular momentum, and the magnetized disk can be possible with a strong magnetic field used from the p-partition argument or by some other mechanism which makes the strong magnetic field on the magnetized. And also recent discovery of the observational beaming of gamma ray burst is naturally consistent with this rotating black hole with the axis. So the proposed structure of central engine has this beaming structure by its construction. And with this beaming, we can try to explain the temporal structure of the gamma ray bursts. Let me show you one of this trial. Since I have no time to discuss, so I'll just show the final result. So there should be some parameters in this analysis. If you allow the wobbling of this accretion disk black hole system, then you can see this the beaming rotation of beaming is very rapid rotation, and the irregularity can be constructed. So this is the observation of this temporal structure, and this is the fit to this observation using this beaming gamma ray bursts, and also the other observation which has quite different structure, but we can reconstruct this temporal structure using this beam. The beaming is very typical nature of this Blandford-Zerniak process. Also, the one more reason why we can explain this very different looking temporal structure is that the Blandford-Zerniak power is decreasing along the rotation axis. So it has one more structure other than the beam profiles. I think that is
for sharing with us your conviction that the source of the light most different power creating and black hole. Other questions or comments? Yes.
What is the basic operation disk you are doing?
Yes, that's a very interesting question. Because I'm not an expert on the accretion disk, I just show you this the mathematically simple structure. So I don't know about the details of the accretion disk.
The reason why I ask you that question is because look at 10^15 Gauss and still you need the density of neutron power almost. Yes. So that is the reason why I ask you that question, because the operation is density can be smaller than that. So
yeah, that's a very good question. And in fact, I don't know much about the accretion disk, so that my answer is very naive. But the first thing, as I told you, the equipartition theorem means that one can at least have that kind of strength of magnetic field in the accretion disk, and that the density means that it relates to the accretion dynamo. It depends on dynamo. We don't know what is the dynamo of the accretion disk or the other things. For example, for the magnetar of the strong magnetic field 10^15 Gauss, we don't know detailed mechanism of its dynamo, how to produce 10^15 Gauss in that neutron star-like object. Okay.
the energy you extract from the black hole side process is in the form of quantum particles.
Yes.
To create energy. How do you convert this energy into time?
That's a very good question that I cannot answer correctly. But I don't know how the point flux can be converted to the shock wave or other energy which can be used to produce gamma ray. So that I think that kind of question has been addressed by and answered by the Usov, for example, how the point flux energy can be converted to this. It's not easy. Yes, that's correct. Yes. Yeah.
You mentioned there Abramovich and Roche.
Yes.
But when you think about it, I don't know the argument, but last year Abramovich was the target. He said that what fails in the Electrodynamics is the initial field. This is what I did with the first question, I think. What was the argument that if you field is low, that it will get relating that more Gauss or the Electrodynamics?
Yes.
You talk about dynamo, but I wonder what was the argument of Fraser or Abramovich.
Yes. So the one point, there are 2 points in the Gaussian Abramovich. That the one is that they compute this, they find a solution of this force-free magnetic sphere of the black hole and the accretion disk system. They find a very rough approximate solution numerically, and they can they can have a solution now. And then the input they are using is the magnetic field on the disk, which is assumed to be the magnetic field by the accretion dynamo, which is naturally small. So in that case, the Electrodynamics process efficiency is very small. So it's based on the magnetic field due to the accretion dynamo. The same is true for the Pringle and Olivi and others. Okay. Thank you.
We go on.
I guess I am the third speaker from the lead family. The subject I'm going to discuss is that the two-dimensional antidistal space and then its discrete the light quantization. The title seems to be unfamiliar to you, but it's also directly related to the four-dimensional isomorphism from black hole. And this subject is strongly motivated by the string theory or the M theory, and well fed into the big framework of the M theory. But this subject itself is interesting in its own light. This subject can be discussed even without mentioning the string theory, because that it is directly related to the four-dimensional rational rods from black hole. So I'll discuss this subject from that point of view instead of the point of view of the string theory. So my instruction, the introduction is rather changed. So this is the angle that I'm looking at, this subject. So there's the intimate relationship between the rational rods from black hole and the ADS2 space, because that in the four-dimensional rational rods from black hole, in the case of extremal case, its metric can be given by this one in the isotopic coordinate. Then if we go to the near horizon limit, or let's look at the low energy limit of the system, then its metric is reduced down to the Bell-Tokyo-Robinson metric. It's nothing but the ADS2 cross S2. So the dynamics of the ADS2 is directly related to the low energy dynamics of the rational rods from black hole. So this is the one motivation. There's also the motivation, strong motivation from the string theory, but I'm not going to discuss much about that point of view. And also this is also the very important subject in the M theory. I think Damo already gave a nice introduction of the string theory. I'll introduce one more subject, so-called D-brane in the string theory. The D-brane is nothing but the hypersurface that the open string can end, and then this is the extended object in modern string theory, and it's in fact the essential component of the black hole in the string worm M theory. The 11-dimensional version, so-called the M theory, we can construct the M brane. Then the usually four-dimensional theory the M theory is constructed by the M5 brane, and then the Kaluza-Klein reduction along the 11th dimension will give us the four-dimensional black hole, and also its near horizon limit is ADS cross S2. And by the light quantization that I'm going to discuss in detail, will give us the ADS cross S2. So the ADS space is also very important in discussing the M brane, the M theory. The whole purpose of this program actually is that to understand the microscopic degree of the freedom of the black hole. In case of the ADS2, is the microscopic degree of freedom of the rational rods from black hole in the low energy limit. For the starting point I'm going to take is that the three-dimensional antidistal black hole. So that's known as the BTG black hole. Its initial is for the initial of the Barnard, Teitelbaum, and Janali. Because the three-dimensional case, we know that what is the microscopic degree of freedom corresponding to the ADS3. So in this case, we now they claim that they know some to some extent the microscopic the underlying theory for the Bekenstein-Hawking entropy or the Hawking radiation, and so on. So that's the starting the point of my study on the ADS2. Since I already mentioned the string theory, I also have to introduce at least at the starting point what this object can be well fitted into the string theory. So this is the half page of half page of the introduction for the string theory, the black hole in string theory. This is the now the so-called in the string community, the classical example of the black hole. So this is the 11-dimensional metric in the string theory, the spore gravity in 10 dimension. So it's compactified on the 4-dimensional tori and then 3-dimensional sphere. So among the 11 dimension, only the meaningful part is this 3-dimensional part, the 3-dimensional space. It's expanded by the t, x5, and then u. U is more like a radial coordinate of this 3-dimensional space. And this is the sphere, and the other part of the other 4 coordinate is compactified on the tori. So this part, this S3 cross T4, this 7 dimension doesn't have actually much of the information of the black hole. All those essential, the low energy dynamics is encoded on this 3-dimensional part. So the 3-dimensional part is important to understand that this 10-dimensional, the black hole object in string theory. And so that's the starting point from the string theory, but we don't actually need too much to understand the string theory. We'll concentrate only this 3-dimensional part. Rewriting these parameters that appear in the string theory, we can understand the 3-dimensional metric is nothing but around the 3-dimensional PTG black hole. So this black hole has the in and outer horizon at the rho minus and rho plus, and also it is charged. It's charged in front of the 2-dimension. So the mass and angular momentum of the black hole is given by this parameter. So this sigma gives us the ratio between the mass and then the spin of the 3-dimensional black hole. And so that 3-dimensional black hole has been studied, the number of the theorists, and now the 3-dimensional black hole is well studied, but it's a 2-dimensional cousin. The ADS2 case is less well understood. So there has been some attempt to discuss that the ADS2 from the ADS3. The early attempt was made by the Strominger and Rowe, and this is the example. This is their attempt. And the idea is that they just applying the conventional Kalajak line reduction. It's very simple. So let us just take a 1-dimensional S1, the compact circle, and then just reinterpreting that 3-dimensional metric in terms of that 2-dimensional metric and then the U1 Kalajak line, the Kalajak line gauge field. So that's so this is just rewriting. It's just rewriting that 3-dimensional PTG black hole. And then this 2-dimensional part is of course describe the 2-dimensional ADS2 black hole, and this is the U1 Kalajak line charge. But what's undesirable feature of this scheme is that it's it means that the color-line reduction is
not be well fitted into this framework, because this describes the size of the S1 circle, but as we approach the infinite boundary, this rho grows just as this radius. So the circle to be compactified in the color-line scheme, its plane cannot be met by this texture. So the color-line reduction is not the suitable framework to the ADS2 from the point of the ADS3. But but still regarding the ADS2 from the quite interesting. So there also has been recent attempts by the Strominger again. It was that instead of taking just a simple color-line approach to he takes the horizon limit first. What he found is that in the horizon limit, I mean that the radial coordinate goes to 0. Where is it, the horizon is located in this coordinate. And then in this limit, when you go to 0, then in this limit, we can see this Dilaton field. This Dilaton field, as goes to 0, this can be dropped, and so this approach the constant. So the color-line reduction maybe work in this case. This was the attempt made by the Strominger, but still in this case we don't know how this underlying theory, I said the boundary conformal field theory is deformed. I'm going to discuss, I'm going to introduce today, as you see here, is that it's a rather kinematic closure. It's so-called the discrete light quantization. This one was advocated by the matrix M theory, but still it's a very promising tool to understand this the ADS2, the gravity from the point of view of the ADS3. Let's just explain this very simple idea. So if we rewrite that three-dimensional metric in the light frame, so this x plus x minus is the coordinate, then its component along the null direction is just constant. So the simple color-line reduction can be well adopted. So as long as we keep this parameter is small, then the color-line reduction does work. Matrix looks like after we take the color-line reduction. Then if we take this color-line reduction, then the x plus and u now is the space, and then this part is that two-dimensional matrix, then it's nothing but this. So the reduction along the line-like direction seems to be the best actually than the reduction along the space-like direction. But the periodic. So now we needed the machinery of the tools of the discrete quantization to have that null-like periodic coordinate. And this is the idea. This is the same idea adopted by the matrix M theory. Suppose we start from the small periodic coordinate x5. So this is the radius x, the RS is a very small number. And then this direction, then we take the Lorentz boost. Then the Lorentz boost, its periodicity along the x plus and x minus is scaled in different ways. Oh, and this becomes expanded. So the idea is that we'll take the RS goes to 0, the while we take the alpha goes to minus infinity, so a large infinite frame. If we start a very small radius amount of the boosting, then in the boosted framework, the x minus the finite periodic coordinate with the finite periodicity. So this is the way we achieved the null-like periodic coordinate. That's the trick we applied, adopted by the matrix M theory. So we exactly adopt that procedure. So this is a very schematic way how this one works. But we start from the small, the periodic coordinate with the small period is the RS, and as we boost it, the system that this endpoint tip goes follow this trajectory, and then this begins to tilt. So goes to in the limit of the boosting. This periodic coordinate, this periodic part begins to approach to this null-like direction. And so to be more precise, introduced it as we defined the discretized coordinate. The reason to introduce this coordinate is that we can trace down the deformation of the system by adopting this discretized coordinate. What ic means that the periodic coordinates in the boosted frame. So every step will have this periodic coordinate, and that's what will take the space line. And this time coordinate is chosen to be also on to the in the large boosting. This t hat approach to the x plus null-like direction, and then the x hat approach to the null-like direction in the x minus prime. So this x hat and t hat is that is well spanned that two-dimensional the space we are interested in. So the rewriting, we rewrite the same metric also in the newly defined discretized coordinate. Then the metric is expect the two-dimensional part is that two-dimensional part is described as ADS2 as we expect. And then this part is to be compactified, and so this black hole was charged by this U1 Kaiser-Klein, the Kaiser-Klein gauge field. But what's the new point? If we carefully apply this light coordinate, is that
we have to transform that the sigma parameter that defines the ratio between the mass and spin of the three-dimensional black hole also has to be transformed according to the disk boosting. So that was the small part, but was very essential to understand this whole procedure. And if we trace back to this procedure, then we can come up to the conclusion that the two-dimensional anti-disk black hole can be described in terms of the extrema, the ADS3 black hole, because that this test can be met into the three-dimensional black hole, but in the three-dimensional black hole, this mass and spin has to satisfy this condition, so it must be the extrema. So the two-dimensional anti-disk black hole can be described in terms of the three-dimensional the BTG black hole in the framework of the LCQ. So now we know how to map the two-dimensional anti-disk black hole to the three-dimensional black hole. So since we already know that the property dynamics of the three-dimensional black hole, so this map tells us that how the two-dimensional black hole can be described. So let's go to the subject of the microscopic theory for the three-dimensional black hole. This is nothing to do, has nothing to do with the string theory. It's more or less related to the conventional Einstein gravity actually. I will take how much about it? Okay. Yeah. The framework that I'm going to take is that the three-dimensional Chern-Simons gravity, but the only reason I took this framework is that this is more convenient than the conventional Einstein gravity. But we can discuss that what I'm going to discuss here also in the framework of the conventional Einstein gravity, because that on the mass shell, the Chern-Simons gravity is equivalent to the Einstein gravity, and all those properties I'm going to discuss in the black hole for the black hole is valid on the semi-classical region. So the same story could be done in the conventional Einstein gravity.
Excuse me, what is the role of charge U1 to describe the Chern-Simons action? No relation at all?
Pardon me?
Charge U1.
Where, this one or this one?
No, in the previous transparency.
No, that
They usually have KK reduction with the U1 charge. What is the relation between that charge and the Chern-Simons action?
This part will tell the answer. Okay, the Chern-Simons gravity is described in the three-dimensional case. The gravity also can be described by this non-abelian Chern-Simons the theory, whose the gauge group is SL12 plus SL2R, and the SL2R gauge group is a linear combination of the dry ion and then the dry ion and the spin connection. So it has the left part and the right part. It's just two copies of the SL12 plus SL2R. And that U1 that appears in the Color-Klein reduction, actually they appear here. It's the same Color-Klein reduction done in the matrix theory also can be repeated in the
this is the way we take represent the Color-Klein answers for this three-dimensional gravity. That U1 is this small U, A mu. And so this is the turbine, and this is the spin connection in the two dimension, and this part is the dilatons, and then this size dilaton, and this A mu is that the U1 color jack line, the gauge field. And using that torsion precondition that appear as a part of the equation of motion, then we also can achieve that the color jack line reduction in this Chern-Simons gravity. That's just the same as the two-dimensional gravity with the Maxwell and then with the dilaton. And so the reason I introduced you to that three-dimensional Chern-Simons gravity is that to show that how that three-dimensional theory can be deformed to the two-dimensional theory, following the DLCQ procedure. That three-dimensional the BTG black hole can be also described by this three-dimensional SL2R cross SL2R Chern-Simons gravity. This is the classical value of the solution. And this is the one copy, and this will be the copy. And what's important? So I already derived that the solution of that BTG black hole in terms of the discrete light on the coordinate. So this x hat and t hat is the same as that appear in the previous transparency. So this alpha is the boosting parameter. So we can trace explicitly how that solution can be deformed following this discrete light quantization. And what the key point here is that the behavior, the observing behavior of the x hat, xt hat is can be gauged away. It's nothing but the gauge degree freedom, so it can be gauged away. But the x hat component cannot be gauged away because the element of this geometry is completely encoded by this holonomy or the Wilson loop that's given by the integral of this x hat. So this is the gauge independent the quantity. So x hat is important. That's important component of this gauge field. Then in the large boosting limit, this as we readily read from this solution, that we can find that the one of the copy of the x hat goes to 0. All this proportional to the exponential alpha. So it just all goes disappear, and the other part is finite. So it means that the one of the SL2R copy just drop, and only the other SL2R remain, and that's enough to describe this two-dimensional space. So to discuss the ADS2 two-dimensional case, we only need the one copy of this at SL2R. So it shows that how the SL2R plus SL2R in 3 dimension can be deformed into the SL2R of the 2 dimension. That's quite plausible because that the ADS3 isometry of the group of the ADS3 is the SL2R plus SL2R, while the isometric group for the ADS2 is just the SL2R. So we need only one copy. So it perfectly goes well with our understanding of the ADS2. I'm not going to discuss much more detail of this underlying theory, but I'll point out just the couple of key points we observed in this DSP procedure. Since this three-dimensional Chern-Simons theory is topological, because in 3 dimension the gravity is topological, so all this the degree of freedom in the bulk can be transmitted to the 2-dimensional theory. Since it's defined on the two dimension,
it could be described by some conformal field theory. And in this case, it's nothing but the West-Minowitz model of SL12 cross SL12. So this is the underlying theory, the microscopic theory for this three-dimensional black hole. And I also already derived this, the underlying the theory on the boundary in terms of that DLCQ coordinate, so we can trace expressly how that the boundaries, that the conformal field theory is deformed along the line of this DLCQ closure. So this is the answer, and so it has two SL12 cross SL12, but its coupling over this interaction or it's asymmetric for this left and right part. That also will tell us that how this theory is deformed. And I'll just bring your attention to this right part that has been dropped in the solution. And this is just the oldest part is talking about the kinetic part, and there is no alpha there. And this is also this one and this one. This part is constrained, and only the Hamiltonian is that defined by the distance. This is the only Hamiltonian for the right part. But as we take the large boosting, exponential minus 2 alpha
goes to infinity. It means that the transition amplitude they described by the action, y action, it's only non-zero for the back-to-back transition, because this whole part is goes to infinity. So it means that on the meaningful state on the right part is just ground
state. Excitation on the right part. So that's the feature of this ADS2 gravity, and this explains the entropy of the ADS2 black hole. And so since this is the two-dimensional theory, the probable state, and then then from that we can black hole based on the microscopic theory. So that has been done for the three-dimensional case. Now we can since we know that the three-dimensional case, we just have to following this passage to describe the two-dimensional case. So following the same procedure for the three-dimensional case, we can take the zeroth component of the bilateral algebra generator of this conformal field theory. Then the occupation number for the left sector is finite. It's still like the exponential for alpha. So the infinity, this is to drop. That's actually what we can show directly. So the right part of this, so entropy only comes from the left part. So this is the Cardi formula to count the number of states in the conformal field theory. So that black hole, the case, the C is that the 6K that can be read from the action we derived, and this NR is that the expectation value of the bilateral algebra. So plug in that number, we found that this right part just goes to A in the large infinite limit, where the ADS2 can be described by the ADS3 metric. So this is the only part for the ADS2. So the ADS2 part now can be this is answered for the ADS2 black hole, and of course this they agree with the results obtained by the other method.
but I can say that this is more like based on the microscopic theory. So it shed some light to understand the gravity on the ADS2. This is the conclusion, but this is much more related to the matrix M theory or the string theory, but so I'm not going to tell you much about this part, but I'm only conclude my talk with one statement. Since more or less we now understand the two, so it may be useful to understand the dynamics.
What they of the rational Rostrom black hole in the low energy dimension.
So the application also to the rational Rostrom black hole in low dimension was described by this framework.
Recently, I already hear Steve Collins gave a very good explanation to black hole entropy in terms of Dirac algebra for any kind of black hole.
Yeah.
What is the relation between your result and this? No connection?
Of course, there should be a connection, but I don't have an answer right now because I'm actually looking at that problem. So generally, it was interesting. So we are working together because he was interested in the three-dimensional the black hole, the frame of the large dimension. So I think that combining with the journalist work with mine might know yet. So we are working. So.
Of my talk is the magnetic Coulomb radiation offense.
Okay. Just one. Okay. Better? Okay. It is not so easy to read, I believe. Magnetic radiation of ultra-relativistic electrons in matter with strong magnetic field. We know that up to now there are no model which can describe production of gamma rays in gamma burst, and I would like to discuss mainly about production of high energy gamma rays in the burst. The plan of my talk is such that at first I would like to discuss the restriction for elementary mechanism for high energy gamma production in gamma ray burst. Of course, this restriction must be come from the observation data. Then some model of the process will be suggested, and this process we can see later.
conservator is in agreement with this restriction I will discuss in first item. Then the result of the accurate calculation for the wide range of the parameter will be given for that mechanism, and as process will be given to show that the suggestion mechanism is very effective for gamma ray assumption.
At first, I would like to discuss some observational data, as I said, and first of all, I would like to remind you, of course you know, but nevertheless, I would remind the maybe not how to reduce the not so good. Okay. Now it is energy spectrum of one gamma burst detected by ICRANet instrument that is the part of GRO space station. And you can see from this example that the energy spectrum is going, or we have in the gamma rays, there are gamma rays up to energy more than 100 MeV. Here 1, 10, and 100 MeV. And this is the spectrum. With spectral index to about minus 2.5. It is not exponential, cut off only such power spectrum. Up to now there are some such events from this and now from another satellite with the registration of high energy gamma rays. I would like to show I would like to show rather old table of the energy of gamma rays, highest energy that was observed in a different gamma burst. Here is the date of the gamma burst, and here is illustrated in this burst. You see, we can see
that in up to GeV or 10 GeV energy. Point out, and important to point out that this burst, if we will see the duration of this burst or another parameters, are the same as another. It is not special class as EV or low energy spectrum and so on and so on. Maybe high energy exists in many bursts, and only the sensitivity of the instrument not enough to register this high energy. I will suggest energy really exists in high energy gamma rays really exist in the burst. And in all these events, the spectrum with similar index, about 8 or 3, but it is not, there are no clear cutoff for any effect. The next fact about the presence of the magnetic field. During a long time, there were a lot of discussion, and from observation of important to see cyclotron light. At first I would like to remind you of Ginga. It is rather old result, and in this result you can see some the energy spectra. You can see some change of the spectrum in some region, and it was, as you know, it was interpreted as cyclotron lines, the first and second harmonics of the cyclotron lines. And energy is 2, and the first harmonics is 20 keV. If we will, or not we, but some people, when people will have convoluted, to is recalculated, this is the count to the energy spectrum, you can see that there are very deep very deep changes in the spectrum of this energy. I would like to mention that the width of these lines is rather narrow. It means the temperature of this system, of this matter, is not so high. It may be plasma or may be matter, but temperature not higher than some keV, and not relativistic case, absolutely not relativistic case. There are some another example also from Ginga. Again, same energy is possible to see for the another gamma burst. Here one also have seen such lines. But as you know, Pescara, on the other hand, has not found similar evidence for such lines. And it was important to have some additional proof to understand, are such lines exist or not exist. And during last period, from November 1994, in the experiment CONUS at the satellite wind, there were registered at least 20 gamma bursts that probably have absorption or emission features. The 3 examples of such burst or such spectrum are given here. And you can see here is the count as a function of the energy, and here is the photon as the number of the photon or energy spectrum after recalculation, taking into account parameters of the instrument. And you can see again the such lines, and again it is rather narrow. Temperature of this medium is not so high, and the energy of this line is given here. It is about maybe 50 kilo electron volts, 40 or 90. For the another dot, the same values. Again, in this case, this
20 those same another characteristics as the timing, as the distribution over the sky, and so on, similar as the total amount of the burst. It means that maybe it is not special class of the burst. Maybe in many cases we have a rather strong field of such type of the gamma ray production or X-ray production.
So, taking into account, we can
say that the system or the region where gamma, I will speak mainly about high energy gamma rays, and we can say that to produce effectively produce gamma rays, the region
and mechanism must be under this limitation or restriction. At first, we see that high-energy particles, maybe electrons or positrons, might be involved with ultra-relativistic particles. Then, some matter must be in the region of the generation, because we see these lines and temperature not so high, so the low temperature matter can be in the region of the production. Maybe plasma, but not non-relativistic plasma. Then, from this line, we can understand that there are very strong magnetic field in this region. From energetic point of view, of course, very convenient or maybe reasonable to have thick target, or in order to produce such conditions that electrons can lose practically all energy in the gamma production. So in this case, we can produce a lot of gamma radiation for the fixed energy of the total energy of the electrons. But if you would like have high energy gamma rays without cutoff, we must have transparency for high energy gamma rays. So for electrons, this region must be thick, or as a thick target. But for gamma rays, it must be as a thin, transparency system. So, if we speak about transparency for high energy gamma rays, how we can reduce it? Of course, first of all, it must be beaming. And in previous reports after lunch, there was discussed about beaming, because if you have not beaming, the maximum energy of electrons will be about some MeV, maybe 10 MeV maximum. Then, because there is a magnetic field, and in order to reduce absorption by pair production of magnetic field, it means that beaming must be not only beaming, but beaming with small pitch angle, between magnetic field and gamma rays. And in order to reduce absorption due to ordinary pair production in Coulomb interaction, the thickness of the material must be rather small grammage, in order to reduce the role importance of this reaction. How we can construct such model or such region? Suppose there is such situation. There is some plasma as a thick target, thick plasma. What does it mean thick? I will say later. Then there is strong field that is smaller than critical field, because we see the energy of the absorption line or cyclotron line. Then it must be beam of the relativistic electrons which are moving along the magnetic field. So it is such construction. Is it possible to construct or not? It is out of the scope of my report. Suppose there is such system, whereas matter, whereas uniform magnetic field with such strength, and there is some beam which accelerated in some region, and acceleration along the magnetic field. Under such condition, usual synchrotron and curvature radiation, because beam
goes along the uniform magnetic line. Sorry. Спасибо. Thank you. Curvature radiation. Of course, the branch travel can be in the system. But besides, there appears a radiation caused by combined effect of matter and magnetic field. The idea was discussed
myself before, and the quantity calculations were made together with Kellner and Begavalov from my institute. So, under such, suppose there is such region, then we can use simple quantum mechanics. In such region, in magnetic field, in such magnetic field, you of course have levels of the energy, and at first all electrons of the beam are at the ground state. Then, due to interaction with the matter, the electrons of the beam can excite to the another level. There are two approximations when two levels only important or many levels important. I will speak at first about these two levels approximation. So, the particle, the beam goes at sometimes due to Coulomb interaction, due to scattering, the electron in transfer movement is excited. If the density is not so high, and if we have such conditions that the number of scattering, of the time between scattering is much larger than the mean lifetime at the excited level, then you have such de-excitation from this level, and in electron system you have usual this expression for the energy, but in laboratory system the energy of gamma will be about 10% or more. It depends on this ratio, maybe order as the primary energy. And we made accurate calculation of this process, calculating cross-section, energy distribution, angular distribution, and so on and so on. And I would like to show some results of self-calculation. This is the cross-section for the exciting of the level number 1 from the ground level under this scattering, and the result is here. Of course, before people calculated such process, and Bussard, for example, have calculated, and the result is given. The difference is that we took into account the screening parameter, the Bay or another screening parameter, so use this formula or this expression for other than
material. So we have this result. Then we, of course, calculated the cross-section for the exciting in other levels. So I would like to show the comparison between cross-sections of the exciting of different levels. It is cross-section for the this from ground to the first level. That is from cross-section from the ground to the more higher level. And you can see that for typical value of the logarithm, which is about 10, the main process is exciting only first level. So you have two levels problem, exciting and de-exciting emission of the radiation. It is if this approximation is good if the density is not so high. It is not as a neutron star itself, but some atmosphere of some object. Then we make all necessary calculations, and I would like result some of the parameters or the characteristics of this process. At first, it is the energy spectrum. It is the energy spectrum in the thin layer when the energy of the electrons is small. This expression and the graph of the energy spectrum is given here. Line number 1 is the energy spectrum or distribution of gamma rays
in this process, and the line number 2 is Bremsstrahlung energy spectrum. And we can you can see the difference, very large difference, because in Bremsstrahlung, in the Feynman diagram, you have additional alpha, which is small. So, as a result, we can calculate the electron energy losses for 1 gram or at the distance dx, and this is the expression for this energy losses that are proportional to the energy of electrons. We can compare the energy losses in this process, which was named by us Magnetocoulomb, compare with the radiation losses. And you can see that this process is about 400 more effective than usual Bremsstrahlung. So angular distribution is of this gamma rays is here. It is green line is angular distribution. Here is theta is the angle of the emission, and gamma is the Lorentz factor of the electrons. And see this one. This one is the angular distribution. Angular. It is important that this parameter is smaller than 10. I will see why important a bit later. Also, this radiation is have linear polarization, and the parameter of the polarization is given, but I believe it is not so important to discuss now because very difficult to measure the polarization for gamma rays. So I will discuss about the angle distribution. For such angle distribution, we can find that the gamma rays can escape from the magnetic field without absorption, because for absorption, these parameters must be equal or more than 10, but we can see that all gamma rays produce with smaller this parameter. So, as a result, you have such a gamma gun. As a gun, you have a gamma beam, very effective for production. But this system, or absorption,
flowing, so it is effective system electrons to the high energy gamma radiation. Of course, the system may be not so thin, and if the thickness of this target is much larger than radiation-less for this process, but much smaller than for usual Bremsstrahlung process. It is there are very wide parameter region when it is possible. Then in this case, we see in such thick model for total absorption of the electrons, we have such energy spectrum. It is important to point out that it is thick model. Nevertheless, that it's not. It is power spectrum. It is power spectrum in thick model because it is thin for gamma rays. And we have calculated the energy spectrum for such rather thick material, and we have this result. If the concentration of the material of this medium is rather high, then the situation more complicated because another level may be. Yes, one approximation, but for thick. All energy
yes, one interaction, another of the same electrons. It is not cascade. If the concentration is rather high, more than 3.10 to the 28 electrons or nucleus in the centimeter cubic, then the scattering is very fast. So another levels can be excited, and I have no time, and maybe it is too long to discuss about all ratio between parameters. But I can say, if we have only simply, we have here the n, it is a logarithm of concentration, and here is the Lorentz factor. Then in this region we have two level approximation that I discussed before. Then here is non-relativistic tensor movement and quasi-classical synchrotron radiation you can use. In this region of the parameters, the movement of transfer movement is ultra-relativistic, but synchrotron radiation is classic. And there are quantum synchrotron radiation, and only for very high intensity, Bremsstrahlung is important compared with this process. So I don't like discuss the spectrum in this multi-layer system. I would like only maybe two conclusion remarks. First of all, if we have not matter but some plasma which are moving in the same direction. In this case, we have the same result, but if plasma have some gamma factor, Lorentz factor, then this expression we must multiply so some factors which are smaller than unity. And if plasma are moving as a total, are moving with velocity half of the light velocity, then it is factor only 1 divided 2, and for this velocity is factor so. In any case, if plasma are moving not relativistically, in any case, this process again much more effective than Bremsstrahlung. And last, we can compare this radiation with curvature radiation. If we have such type of the line, not strictly uniformly, but with some curvature, you have curvature radiation. And let us compare the efficiency of two mechanisms which are discussed and curvature radiation. For this estimation, we must know the density of the matter. The density of the matter we can estimate from such. For the effective thickness for this mechanism to convert energy from gamma ray, from electrons to gamma rays is such. Only 0.1 or 0.2 approximately gram per centimeter square. The dimension of the volume of the region we can estimate from the variation of the intensity. That is about 10 to the 7 or maybe 3 multiplied to the 7. And from this we have this concentration. So the curvature radiation for such concentration will be important only if the curvature is smaller than this 2.6 centimeters. In either case, this the role of the mechanism I discussed more and more important than curvature radiation. So I don't know how to produce such region, but if you have some model and it is possible to construct such region, it is very effective system for high gamma ray production. and for escape of gamma ray production for this region. Thank you.
Thank you, Kotel, to give us a scenario of production of gamma rays.
Do you have any evidence for polarization of gamma ray burst?
For evidence for?
Polarization of gamma ray
No, not of course not. It is very difficult. It is very difficult to measure gamma polarization. It is possible, in principle, to measure the gamma polarization of gamma quantum. We can discuss it using the pair production. It is possible to see the process. In principle, I can
discuss how to measure polarization. Maybe just now, maybe later. Possible to see converter very thin. The test. Oh, not this one. Okay. It is possible to use the if you have gamma ray, you have electron-positron pair, and the position on the linear polarization. It is possible to register the plane of the electron-positron. It is possible, but multiple scattering is so important to measure, and it is necessary to have very many times. In principle, it is possible to measure a linear. You reach the gamma ray so at only in 1997. If there is any reason you stop my link, why? Yes, it is many new arguments for this. Yes, you are quite correct. But these arguments in the same direction. There's a beaming, and you discuss about beaming, yes, you're quite correct. But it is in the frame or in this picture. Yes, it may be, yes, beam of electrons, of course, maybe, yes, some beam. Yeah, in any acceleration.
Then you have a target, and this analysis is quite interesting. But I would like to stress that in gamma rays, first, very likely, we have of the order of 10 to the 54 Earths. Namely, this plasma of plasma
solo control. Its own control. It's not the its own dynamics, as its own control, as its own physics, because you have the system of plastic magnets and gamma, which is colossal, and the beam is not a good approximation, but this is just a comment.
I understand.
The comment is not, I don't want to, it's just a comment that starting your picture, the first thought, let's take a beam. Okay, this in my opinion is good for this, but it's not good for the gamma ray.
No, I'm not agree with you. Sorry, I'm not agree with you. Why? Yes. If you have the case of the DC, and you put the beam of the electron to the target, you have high energy. You have Bremsstrahlung, and you have the pair production. And the typical length or typical cross-section are the same. So you have a cascade in this system. And you have cutoff on the energy. If the production of the gamma rays is effective, then and production of pairs is effective, and you have no, at the output, you have no high energy gamma rays. In this case, situation is another. You have mechanism which 400 times more effective for gamma production than Bremsstrahlung, but there are no such. That is the first. So it means it is not the same situation. It is not a cascade. It gives us opportunity to escape cascade. That is the first. Now about the beam. Of course, it is the question. But if you have some experimental result with energy more than 10 GeV, it is difficult to understand how possible to escape of such gamma rays from small distance, because we know the maximum size.
How possible to escape against gamma production without beaming? Beaming must be.
I don't want to look at the implication. I want to do a model. Making a model, I don't think you can consider the first step, the beam. The beam cannot be considered as such, because a flux of so much plus or minus z as its own value. And its own value I would say is wrong.
But we know that in many cases, we know many examples. Nevertheless, we just yes, of course, it is speculation, but we know in many cases. For example, we know jet. It is beam. For example, it is beam. It's okay. In neutron star, it is also beam. Okay. This one.